All right, in this example, example 11, we're going to be looking at a, particular type of transformation from R5 to R4. Uh, the matrix A and the test vector V1 are given. So I'm going to go ahead and compute those there. So here's the transformation A. This is the corresponding transformation matrix for key. And so the first part of what we want to do is, for A, is to compute the transformation of the vector V1. So that assumes we simply need to multiply A times V1, and that gives us then that the value of the transformation is an R4 vector, which is what we expected, 15, 13, 8, and 8. Okay, so that's, if you will, the new location of the new transformation. So it went from R5 to R4. Some sort of hyperplane in R5 to a hyperplane in R4 with new coordinates 15, 8, 13, 8, and 8. Okay. And then the next one, we need to calculate the nullity of the transform from part B. Okay, so the nullity, remember, means that we need to find the kernel and then look at the dimension of the kernel for this transformation. Okay. So if we augment the matrix A with uh, the column of zeros that correspond to the homogeneous solution or the zero vector. We could also just think about writing the echelon form of A and imagining that that column of it, it's the augmented matrix that we're really referring to. So if we go ahead and type in the echelon form, okay, you're going to see here you get that it's an R4 matrix or an R4 vector. So immediately you should see that that means that x5 is, there's no value of x5, right? So that x5 is a free variable, free parameter. So x5 can be anything, okay? And then it says that um, the remaining vector uh, can be written as a linear combination. So this uh, fifth vector here, and it's funny because this is one of the rows, right? But it actually is also the fifth vector. So this fifth vector here is a linear combination of the other four vectors. So the four vectors will span R4. This is a linear combination of those. Okay. And so we have this free space to compute the nullity. And so if we do back substitution, right, if we look at this, this is uh, X, or you can call it maybe C4 and C5, right? This is C1, C2, C3, C4, C5. This is equal to the zero vector, so or there should be another column here for the augmented matrix. So to solve this for C4, I would subtract 35 over, so I would get that C4 is equal to negative 35. If I plug that back in and multiply, I get 5 into negative 35 is negative 7 times 2 is negative 14. This is C3 minus 14 equals 0. Adding that 14 over, you're going to get C3 is equal to 14. And likewise, if you back sub in for the other two C's, you'll get the following vector for the kernel space. So you're going to have, call it V, no, U, no, X. Let's call it the vector X. This is going to equal matrix. And so the resulting values you see here are going to be 55 over 3. Let's see, 77 over 6, which was not the value I was expecting, given the nice numbers at the beginning, negative 35. And since the free parameter C5, if you will, it can be anything, we usually just set it equal to 1 to indicate that it's there. And so this vector, okay, there it is, there's X, is really some scalar multiple, so C times X. And so the kernel of this space is this vector. Here it is, 55C. You can pull the C out, right? So it's basically, it's not basically, it is literally this times C. This is the kernel of it. And so since there's only one vector in the space, the nullity of this vector, or the nullity of the transformation, is 1. Okay, all right, I hope that was helpful, and I'll see you in the next video.